The universe is silent, but our questions echo across the cosmos. We have stared into the night sky for millennia, wondering if we are truly alone. While we still lack definitive proof of life beyond Earth, humanity has crafted a mountain of profound and tantalizing questions. Today, we are going to explore 30 of the most intriguing puzzles about alien existence. By the end, you will not just hear the questions, you will understand the scientific mysteries and staggering possibilities behind each one. We will wrestle with why we have not found anyone yet and imagine what the first alien microbes might be like. What is the one question about alien life you secretly hope we answer first? The silence of the cosmos is the loudest mystery we have. This is the first and greatest question, the one that has haunted humanity for generations. Are we truly alone in the universe? On one hand, the numbers are overwhelmingly in favor of life. Our galaxy alone contains hundreds of billions of stars. Many of those stars have planets, and we now know from telescopes like Kepler and TESS that rocky worlds orbiting in the habitable zone where liquid water can exist are incredibly common. With potentially billions of Earth-like planets in our galaxy and trillions of galaxies beyond it, the sheer scale seems to make our solitude impossible. It feels like a mathematical certainty. This is the heart of the famous Drake equation, a formula that tries to estimate the number of detectable civilizations in our galaxy by considering factors like star formation rates and the odds of life developing intelligence. Even using very conservative numbers, the result is rarely zero. The universe appears built for abundance, yet this optimism crashes directly into a wall of silence known as the Fermi Paradox. Enrico Fermi, a brilliant physicist, famously asked a simple question over lunch one day. If the universe is so vast and old and intelligent life is probable, then where is everybody? Where are the ships, the signals, the undeniable evidence? Our telescopes see no giant interstellar engineering projects. Our radio dishes hear no welcome messages. The cosmic calendar, which compresses the universe's history into a single year, shows that Earth formed relatively late. If another civilization arose just 1% earlier than us on that cosmic timescale, they would have had millions of years to expand across the galaxy. They should be everywhere by now, so we are left balancing two powerful, conflicting ideas. The mathematics of probability screams that we cannot be the only ones. But the profound and unbroken quiet all around us whispers that maybe, just maybe, we are. This paradox is the foundation upon which every other question about alien life is built. This leads us directly to our second great puzzle. If life does exist out there, what would it actually look like? Would we even recognize it? On Earth, the force of evolution has crafted an astonishing diversity of forms, but they all share a common blueprint. Every creature, from the tiniest microbe to the largest whale, is built from carbon-based chemistry, uses liquid water as its solvent, and encodes its genetic information in molecules like DNA. This is our only example, so it is natural to assume life elsewhere would follow a similar path. This idea is called convergent evolution, where similar environmental pressures lead to similar solutions. Think of the streamlined shape of a shark, a dolphin, and an extinct marine reptile called an ichthyosaur. They are not closely related, but the physics of moving efficiently through water sculpted them all into similar forms. On an alien world with oceans, mountains, and an atmosphere, we might expect to see familiar adaptations. Creatures with eyes to sense light, limbs to move across terrain, or wings to ride the air currents. The alien equivalent of a crab or a squid seems almost inevitable on any watery world. But this is where the true mystery deepens. What if alien life is built from an entirely different foundation? Scientists speculate about the possibilities of alternative biochemistries. Could life be based on silicon instead of carbon? Silicon sits right below carbon on the periodic table and can form many similar bonds. On a hot, rocky world, silicon-based life might thrive in conditions that would incinerate us. Or perhaps on a frigid moon like Titan, life would use liquid methane or ethane instead of water, with ammonia playing a role in its cellular processes. These would not be creatures as we know them. A silicon-based organism might have a crystalline structure, growing slowly and living for millennia. An ammonia-based life form might have a chemistry that functions at temperatures hundreds of degrees below zero. Their very perception of reality, their senses, their experience of time could be utterly alien to our own. Then we push the boundaries even further. Could there be life that does not rely on chemistry at all? Plasma-based life forms dancing in the atmospheres of stars, or information-based entities existing as patterns in a planet's magnetic field. These are far more speculative, but they remind us that our imagination is limited by a single data point. The concept art we see in science fiction, from the towering, six-legged creatures of Avatar to the shimmering, energy-based beings of Star Trek, are all attempts to answer this question. They blend the familiar logic of adaptation with the thrilling possibility of the utterly unknown. So when we dream of meeting aliens, we must ask ourselves, are we hoping to shake a hand, or are we prepared to communicate with a sentient, floating cloud of gas or a living, thinking geological formation? The answer will redefine what it means to be alive. The search for life begins with a map, and our cosmic map is filled with promising coordinates. The first place we look is right in our own cosmic backyard, our solar system. Mars stands as our most immediate and compelling target. While its surface is a cold, arid desert today, overwhelming evidence tells us it was once a very different world. Orbital images reveal ancient river valleys, lake beds, and minerals that can only form in the presence of liquid water. The question is not whether Mars had the ingredients for life, but for how long and whether life ever took hold. Current missions are not looking for little green Martians, but for fossilized microbes in ancient rocks, or more excitingly, for signs of life that may still exist today, hidden away in deep, briny aquifers beneath the frozen soil, shielded from the harsh radiation above. Beyond Mars, the most tantalizing possibilities lie not on planets but on moons. Jupiter's moon Europa is a world encased in a global shell of ice, but beneath it, scientists are confident there churns a vast, salty ocean containing more liquid water than all of Earth's oceans combined. The heat to keep this ocean liquid comes from the gravitational tug of war with Jupiter, which flexes the moon's interior. On Earth, we find life thriving in the absolute darkness of deep-sea hydrothermal vents, drawing energy from chemicals, not sunlight. Europa could have its own vents, its own deep, dark ecosystems. Then there is Saturn's moon Enceladus, a small, icy world that actively sprays its subsurface ocean into space through giant geysers at its south pole. Spacecraft have flown directly through these plumes and detected organic compounds, the building blocks of life. We could potentially sample this alien ocean for signs of biology without ever drilling through the ice. And we cannot forget Titan, Saturn's largest moon, shrouded in a thick, hazy atmosphere. Titan is the only other place in the solar system with stable liquid on its surface, but its rivers and lakes are not water, they are flowing methane and ethane. This introduces the concept of the weird life scenario, where life might use liquid methane the way we use water. A probe has already landed on Titan's surface, and future missions aim to sail its alien seas. Venturing beyond our solar system, the search expands to exoplanets, worlds orbiting other stars. The key is the habitable zone, often called the Goldilocks zone, where a planet is neither too hot nor too cold for liquid water to exist on its surface. Telescopes like the James Webb Space Telescope are now analyzing the light filtering through the atmospheres of these distant worlds, looking for chemical fingerprints known as biosignatures. A biosignature is a substance, like oxygen or methane in specific combinations, that is strongly suggestive of biological activity. On Earth, our atmosphere's abundant oxygen is a product of life, a continuous gift from plants and microbes. Finding a similar imbalance on an exoplanet would be a revolutionary clue. And then there are technosignatures, signs not of simple life but of advanced intelligence. This could be a narrowband radio signal like a cosmic beacon, or the unusual light pattern of a massive artificial structure, like a hypothetical Dyson sphere built around a star to capture its energy. So our search is a two-pronged mission, scanning the chemical compositions of alien atmospheres for the whispers of biology, while simultaneously listening on every frequency for a deliberate hello. The most likely answer to the great question is not a towering intellect, but a silent, microscopic one. If we ever find definitive proof of life beyond Earth, our first encounter will almost certainly be with microbes. This may sound like a letdown after dreaming of interstellar civilizations, but it would be the single most important discovery in human history. It would shatter the paradigm of our cosmic loneliness and prove that the spark of life can ignite elsewhere. To understand why microbes are our best bet, we look to the most resilient life forms on our own planet, the extremophiles. These are microscopic organisms that thrive in conditions we once thought were utterly sterile and lethal. We find them boiling in the acidic springs of Yellowstone, frozen solid in Antarctic ice for millennia, flourishing in the crushing, sunless depths of ocean trenches, and even surviving the vacuum of space clinging to the outside of the International Space Station. The champion of this resilience is the tardigrade, also known as the water bear, a microscopic animal that can withstand radiation, extreme heat and cold, and decades of complete dehydration, entering a state of suspended animation until conditions improve. The existence of extremophiles dramatically expands our concept of the habitable zone. It tells us that life is not a delicate flame, but a tenacious spark that can take hold in the most unexpected corners of a world. An alien planet does not need Earth like oceans and forests to host life. It might only need a sliver of liquid water trapped in rocks or a chemical energy source deep underground. This shifts our entire search strategy. The challenge, of course, is detection. We cannot point a telescope at a distant exoplanet and see its bacteria. Even within our own solar system, confirming the existence of microscopic life is a monumental task. A rover on Mars might see a strange rock formation, but is it a fossil or just an odd mineral deposit? It might detect organic molecules, but are they the leftovers of ancient biology or just chemistry without life? This ambiguity is why sample return missions are the holy grail of astrobiology. The plan for Mars involves a sophisticated robotic fetch quest where a rover collects carefully selected soil and rock cores, seals them in ultra-clean containers, and launches them back to Earth. Only in our most advanced laboratories, with instruments far too large to send on a rover, can scientists perform the exhaustive, destructive tests needed to hunt for the subtle, definitive signatures of past or present life, like the specific structures of cells or the isotopic fingerprints of biological processes. Finding an alien microbe, even a fossilized one, would answer the fundamental question forever. Life is not a miracle unique to Earth, it is a cosmic imperative. And if simple life is common, then the door is flung wide open for the next, even more profound question: what happens when microbes have billions of years to evolve? But finding a microbe is only the first chapter. The true revolution begins when we ask what happens next. What if we do not find simple life but intelligence? This is the fifth and perhaps most staggering question on our list. Intelligence is a spectrum, not a single point. On Earth, we see glimmers of it in many creatures, from crows using tools to dolphins using complex communication. An alien species might be at a similar stage to our own early hominids, just beginning to shape their world. Or they could be a civilization that mastered agriculture and built their first cities while dinosaurs still roamed our planet. The scale of cosmic time allows for possibilities that strain our imagination. A species just 1 million years more advanced than humanity would possess technology indistinguishable from magic to us. They might have solved aging, harnessed the energy of stars, or learned to manipulate the fabric of spacetime itself. Their art, their philosophy, their very understanding of reality would be as incomprehensible to us as a smartphone would be to a cave painter. So how would we ever make contact with such a being? The most plausible first encounter would likely be indirect. It could be a signal. For decades, projects like SETI, the search for extraterrestrial intelligence, have been listening for a deliberate broadcast, a cosmic beacon meant to announce we are here. The most famous candidate is the WOW signal, a powerful narrowband radio burst detected in 1977 that matched the predicted signature of an interstellar transmission. It came from the direction of the constellation Sagittarius and lasted 72 seconds, but it was never heard again. Was it a fleeting glimpse of an alien transmitter, or just an unexplained natural phenomenon? We still do not know. Contact might also come in the form of an artifact. Imagine our probes billions of years from now, stumbling upon the ruins of a long-dead civilization on a distant moon, a silent monument to a species that rose and fell before our sun even ignited. Or perhaps we would detect a technosignature, the evidence of massive engineering. Astronomers have scanned stars for signs of Dyson spheres, hypothetical structures built to encase a star and capture nearly all its energy. A star that flickers in an unnatural way, dimming in specific patterns, could be our first clue that someone out there is building on an unimaginable scale. The most dramatic and least likely scenario is direct visitation. The distances between stars are so vast that physical travel seems implausible for any civilization bound by the laws of physics as we understand them. But if a species is millions of years ahead of us, they may have discovered shortcuts we cannot yet dream of. The implications of any contact would redefine humanity. A signal would tell us we are not alone in the universe, but it would also place us in a cosmic community, potentially one with rules, histories, and hierarchies we know nothing about. It would be a moment of profound humility and boundless curiosity. The message we sent from the Arecibo telescope in 1974, a simple pictorial broadcast containing basic information about humanity and our solar system, was a child's first whisper into a dark forest. The answer, if it ever comes, could be a library. But that profound hello, if it ever arrives, presents an even greater puzzle than silence. How would we even begin a conversation with a mind that evolved under a different sun? The distances alone make simple dialogue impossible. A radio signal sent to a star 100 light-years away would take a century to arrive and another century for any reply to reach us. A single exchange of greetings would span the lifetimes of everyone alive today. This is not a phone call. It is a message in a bottle tossed into a cosmic ocean with the hope that someone someday might find it and understand. Our primary tool for this has been radio waves, which travel at the speed of light and can penetrate the dust between stars. But radio signals weaken dramatically over distance, spreading out into a whisper that gets lost in the background noise of the universe. A broadcast from Earth, like our television and radio transmissions, becomes an indecipherable static hiss within just a few light years. To be detected across interstellar space, a message must be powerful, focused, and intentionally designed to stand out. This is where the real work of xenolinguistics, the study of alien language, begins. We must construct a message that transcends biology and culture. Many scientists believe the universal language is not English or Mandarin, but mathematics and physics. The laws of the universe are the same everywhere. A civilization advanced enough to build a radio telescope will understand prime numbers, the structure of the atom, or the unique radio frequency of hydrogen, the most common element in the cosmos. Our first deliberate interstellar messages used this logic. The Pioneer plaques attached to the Pioneer 10 and 11 spacecraft used simple pictorial symbols to show a map of our solar system, the position of Earth, and diagrams of a human man and woman. The later Voyager golden records went further, containing sounds and images selected to portray the diversity of life and culture on Earth, from a baby's cry to Bach, all with pictorial instructions on how to play them. Some proposals are even more abstract, like a language called Linkos, designed to start with basic mathematical concepts and gradually build up to complex ideas about human society and morality. There is a more radical idea, sending the blueprint for life itself. We could transmit the entire human genome, a digital code that describes every protein that builds a person. An advanced civilization with the technology to receive and decode it could, in theory, reconstruct a human being from the atoms up. It is the ultimate self-portrait, but also a deeply unsettling one. This leads to the most heated debate in the field, known as METI, or Messaging Extraterrestrial Intelligence. While SETI listens, METI actively shouts. A small number of scientists have beamed powerful, targeted messages at nearby star systems. Critics, including the late Stephen Hawking, have warned this is dangerously naive. They compare it to a child shouting in a dark, unknown forest. If an advanced civilization exists, its intentions are a complete mystery. History on Earth shows that when a more advanced culture encounters a less advanced one, it seldom ends well for the latter. Proponents argue that any civilization capable of interstellar travel would already know we are here from our accidental radio and television leakage, so we might as well be polite and say hello properly. The debate has no easy answer. Is broadcasting an act of hopeful courage or reckless hubris? In trying to solve the puzzle of communication, we are forced to confront the deepest questions about our own nature and our place in a universe we are only beginning to understand. That debate over shouting into the dark forest brings us to a far more tangible mystery, one that has moved from the fringes of culture to the halls of government. What are UFOs, or as they are now officially called, UAP? For decades, the term UFO, or unidentified flying object, was synonymous with little green men and flying saucers, a staple of science fiction and tabloid headlines. It carried a heavy burden of stigma, making pilots, military personnel, and scientists reluctant to report strange sightings for fear of ridicule. This changed with a simple but powerful shift in language. The modern term is UAP, which stands for Unidentified Anomalous Phenomena. This is not just a rebranding, it is a scientific framework. Anomalous means it does not fit known patterns. Phenomena is a neutral term for an observable event. A UAP is simply something in the sky, in space, or even underwater that cannot be immediately identified as a known aircraft, whether balloon, drone, or natural event. It is a data point, not a conclusion. This shift in language opened the door for serious investigation. In 2021, the United States Office of the Director of National Intelligence released a landmark report. It was a sober, 9-page document that acknowledged what many witnesses had claimed for years. Of 144 military UAP reports investigated, 143 remained unexplained. The report explicitly stated that some UAP appeared to demonstrate advanced technology, exhibiting flight characteristics unknown to the United States. They could move with no visible means of propulsion, accelerate instantly, and operate across different domains from air to water with ease. This was not a declaration of alien visitation, but a monumental admission, the government saying, "We see these things too, and we do not know what they are." To understand the weight of this, we must look at a specific case like the 2004 Nimitz incident. Over several days in November, the USS Nimitz Carrier Strike Group was conducting training off the coast of San Diego. Advanced radar systems detected multiple objects descending from 80,000 feet to hover just above the ocean in a matter of seconds. Fighter pilots were scrambled to intercept. One pilot, Commander David Fravor, described a white, tic-tac-shaped object about 40 feet long, with no wings, no exhaust plume, and no visible propulsion. It mirrored his movements, then accelerated away at a speed he said was like nothing he had ever seen, disappearing from sight in an instant. Another pilot's jet later captured infrared video of a similar object, the now famous tic-tac video, showing it maneuvering in ways that defy our understanding of aerodynamics. The official stance is not that these were alien spacecraft, but that they are truly unidentified. The balanced analysis considers all possibilities. They could be secret, next-generation technology from another nation, a possibility that carries significant national security concerns. They could be rare atmospheric plasma phenomena or tricks of sensor fusion and perception. But the most intriguing possibility, the one that forces us to keep an open mind, is that they represent something entirely outside our current scientific catalog. The shift from UFO to UAP is a journey from fantasy to forensic inquiry. It is the recognition that some mysteries in our own atmosphere remain stubbornly, thrillingly unsolved. The line between unexplained phenomena and ancient myth is surprisingly thin. This brings us to our eighth question: have aliens already visited Earth? The idea is captivating, suggesting that our distant ancestors were not just building pyramids and temples, but were recording encounters with beings from the stars. Proponents of the ancient astronaut theory point to enigmatic artifacts and monuments that seem to defy the technological capabilities of their time. In the high desert of Peru, the Nazca lines stretch for miles, massive geoglyphs of animals and geometric shapes so large they can only be fully appreciated from the air. The theory asks, who are these designs for, if not for visitors flying above? In the Mediterranean, the Antikythera mechanism, recovered from a 2,000-year-old shipwreck, is an astonishingly complex bronze device of gears and dials, often called the world's first analog computer. It could predict astronomical positions and eclipses with remarkable precision. To some, its sophistication appears anachronistic, a piece of advanced knowledge that seemingly dropped from the sky into the ancient world. The scientific explanations, however, are equally compelling and grounded in human ingenuity. The Nazca people could have created their lines using simple surveying techniques, stakes, and ropes, building the designs incrementally over generations as part of religious or astronomical rituals meant for their gods in the sky, not physical pilots. The Antikythera mechanism was not magic, but the pinnacle of Hellenistic engineering, a testament to a lost lineage of mechanical genius that we are only now rediscovering. It proves that ancient civilizations possessed a profound and sophisticated understanding of the cosmos, developed through centuries of observation. So why does the alien explanation persist? It often stems from a subtle underestimation of our ancestors, a reluctance to grant them the full credit for their own awe-inspiring achievements. Yet, even if these artifacts are not proof of visitation, the underlying question remains valid from a cosmic perspective. If an advanced civilization existed in our galactic neighborhood, even millions of years ago, could they have come here? The vast timescales of the universe make it possible. Earth has been a living, watery world for nearly 4 billion years, a passing survey probe from a civilization that rose and fell while life on Earth was still single-celled could have come and gone, leaving no trace we would recognize. This leads to two fascinating and slightly unsettling hypotheses about why we might not see them today. The first is the zoo hypothesis. Imagine our solar system as a vast galactic wildlife preserve. An advanced civilization, perhaps a coalition of many species, could have long ago discovered Earth and its budding intelligent life. They might have established a prime directive of non-interference, placing us in a kind of cosmic quarantine. They observe us from a distance, hidden by technology we cannot perceive, allowing our civilization to develop naturally without influence or panic. We are the exhibit and they are the quiet curators. The second idea is the quarantine hypothesis, which has a darker tone. Perhaps advanced civilizations are common, but they have learned a terrible lesson. They may have discovered that emerging intelligences are inherently dangerous, either to themselves or to others. Maybe every young species goes through a volatile, self-destructive phase with technologies like nuclear weapons or artificial intelligence. To protect the wider galactic community, older civilizations might impose a strict embargo, a cordon sanitaire around planets like ours until we prove we can survive our own adolescence without causing catastrophe. In both scenarios, the silence is deliberate. The lack of contact is not a sign of our loneliness, but a policy. The night sky feels empty because we are being watched, studied, or contained. It is a humbling thought that reframes our entire search. We are not just looking for signals in the dark. We might be living inside a bubble of intentional silence, waiting to see if we are worthy of an introduction. That cosmic silence we feel is not just a mystery, it is a mathematical puzzle. In 1961, astronomer Frank Drake sat down to prepare for the very first scientific meeting on the search for extraterrestrial intelligence. He wanted a way to structure the conversation, to break down the enormous question of, are we alone, into a series of smaller, more manageable probabilities. What he created was deceptively simple, a single line of multiplication that has since become the most famous equation in the search for alien life, the Drake equation. It does not give us a single answer, but it frames the entire debate. The equation is written as n equals r star times fp times ne times fl times fi times fc times l. That looks intimidating, but each letter is just a step in a cosmic detective story. Let us walk through it together. N is the number we are trying to find, the number of civilizations in our Milky Way galaxy whose electromagnetic signals we could potentially detect right now. The first term, r star, is the average rate of star formation in our galaxy. How many new stars like our Sun are born each year? This is a number astronomers can measure fairly well. Current estimates suggest our galaxy forms about 1.5 to 3 new stars annually. Next is FP, the fraction of those stars that have planetary systems. For decades, this was a giant question mark. We did not know if planets were common or rare. Today, thanks to missions like Kepler, we know planets are not just common, they are ubiquitous. Nearly every star we look at seems to have at least one planet, so FP is now very close to 1. Then comes NE, the average number of planets per star system that are in the habitable zone, where conditions could allow for liquid water. This is where the numbers get exciting and uncertain. We have found thousands of exoplanets, and a significant fraction of them are small, rocky worlds orbiting in their star's Goldilocks zone. Conservative estimates suggest there could be at least one such world for every few stars. Our galaxy may harbor tens of billions of potentially habitable planets. Now we reach the great leap, the transition from chemistry to biology. FL is the fraction of those suitable planets where life actually emerges. This is the first variable in the equation where we have absolutely no data. Is life an inevitable chemical process given the right ingredients and enough time? Or is it an astonishingly rare fluke? On Earth, life appeared relatively quickly after the planet cooled, suggesting it might be common. But we have no proof it happened anywhere else. Then, Fi is the fraction of those life-bearing planets where intelligence evolves. Intelligence, as we define it, is not a guaranteed endpoint of evolution. On Earth, it took billions of years and emerged only once. Is intelligence a cosmic imperative or a quirky accident? FC is the fraction of those intelligent civilizations that develop technology to broadcast their presence into space, like radio telescopes. And finally, L is the length of time such a civilization releases detectable signals into the cosmos. This is perhaps the most sobering variable. A civilization might broadcast for only a brief, volatile century before succumbing to war, environmental collapse, or simply moving on to technologies we cannot detect. Or they might broadcast for millions of years, The power of the Drake equation is that it shows us where our knowledge ends and our speculation begins. Plug in optimistic numbers where life and intelligence are common and civilizations are long-lived, and n can be in the thousands or even millions. The galaxy should be buzzing with conversation. But use pessimistic numbers where the steps to intelligence are incredibly unlikely or civilizations self-destruct quickly, and n can be heartbreakingly small, even less than 1, meaning we might be the only one right now. Modern discoveries have filled in the early terms with solid numbers, making the galaxy seem wonderfully crowded with potential. Yet the later terms remain profound mysteries, locked in the biology labs and history books of worlds we may never see. The equation does not tell us we are alone, but it tells us exactly why we do not know. It is a map of our own ignorance and a beacon guiding every search of the silent sky. The Drake equation maps our ignorance, but the silence it describes has a name. This is the Fermi Paradox, a contradiction so sharp it has defined the search for alien life for generations. It all started with a simple lunchtime question. In the summer of 1950, physicist Enrico Fermi was chatting with colleagues about flying saucers and the possibility of faster-than-light travel. The conversation turned to the sheer number of stars in the galaxy. Given the age of the universe, Fermi reasoned, any civilization with a modest head start should have had more than enough time to spread across the entire Milky Way. He looked up and asked the question that has echoed ever since. Where is everybody? His point was devastatingly logical. The universe is about 13.8 billion years old. Our galaxy formed not long after. Our solar system is a relative newcomer at 4.6 billion years old. If another intelligent species arose just 1% earlier on the cosmic calendar, they would have had a 10 million year head start. With even a fraction of the speed of light, self-replicating probes could explore or colonize every star system in the galaxy within a few million years. They should be everywhere. Their artifacts should be in our solar system. The sky should be filled with their signals, yet we see nothing but empty space and silent stars. This is the paradox. The high probability of alien life clashes violently with the total lack of evidence for it. Over the decades, scientists and thinkers have proposed dozens of solutions to this puzzle, each one a different story about the nature of life and intelligence in the cosmos. One of the most sobering ideas is the Great Filter. This theory suggests that there is at least one enormous, nearly insurmountable barrier that prevents life from progressing to the stage where it fills the galaxy. The terrifying question is, where is this filter located? Is it behind us? If the filter is something like the transition from non-living chemistry to simple life, then we are the miraculous exception and the galaxy is mostly sterile. This would be good news for humanity. But if the filter is ahead of us, then it is something that dooms almost all intelligent civilizations before they can expand. This could be a technological catastrophe we have not yet faced, like nuclear war, a runaway artificial intelligence, a bioengineered plague, or the societal collapse that comes with discovering a universe-shattering truth. We may be blissfully unaware that we are approaching a cliff that nearly everyone else has fallen off. Another solution is the rare Earth hypothesis. This argues that while simple microbial life might be common, the specific conditions needed for complex, intelligent life are extraordinarily rare. It is not just about being in the habitable zone. It might require a large moon to stabilize the planet's tilt and climate, a magnetic field to shield against radiation, the right kind of star, the protective influence of giant planets like Jupiter to deflect asteroids, and a geological history that allows for continents and plate tectonics. According to this view, Earth is not a typical rocky world. It is a cosmic jackpot, a perfect storm of rare events. We are not hearing from anyone because almost no one else made it this far. Then there are solutions that suggest the aliens are here, but we simply cannot perceive them. A civilization millions of years more advanced might use technologies that are indistinguishable from natural phenomena to us. Their communications might not use clumsy radio waves, but something like quantum entanglement or manipulations of spacetime itself. Or they might have transcended physical form entirely, uploading their consciousness into a planetary-scale virtual reality, leaving the physical universe quiet and empty. They are not gone, they are just playing a different game in a realm we cannot access. Perhaps they are observing us under a zoo or quarantine protocol, as we discussed earlier, choosing to remain hidden. Or maybe the galaxy is already full of life, but it is mostly microbial or non-technological, with intelligent tool users like us being the oddity. Each solution to Fermi's question paints a different portrait of our cosmic neighborhood and our own future. It forces us to ask, are we pioneers, survivors, or inmates? The silence is not an answer, but a mirror reflecting our deepest hopes and fears back at us. Perhaps the most mind-bending solution to the great silence is that we are not looking out at a real universe at all. What if our entire reality, from the farthest galaxy to the feeling of sunlight on your skin, is an elaborate simulation, a cosmic video game created by a hyper-advanced alien civilization? This is not science fiction anymore, but a serious philosophical argument known as the simulation hypothesis, most famously proposed by philosopher Nick Bostrom. His logic is startlingly simple. If any civilization anywhere in the universe reaches a post-human stage of technological maturity, they would likely possess computing power beyond our comprehension. One potential use of that godlike power would be to run detailed simulations of their own history or of imagined worlds for research, entertainment, or even as a form of ancestor worship. These simulated realities would be populated by conscious, thinking beings who believe their world is real, just as we do. Now, if such simulations are possible and even a single civilization runs many of them, the number of simulated minds would quickly dwarf the number of biological original minds. Statistically, therefore, it is far more likely that we are living inside one of those countless simulations than in the base physical reality. This idea reframes the Fermi Paradox in a startling way. We do not see aliens because the aliens are outside the simulation running the program. They are the programmers, the architects of our cosmic rules. The strange quantum fuzziness at the heart of physics, the fact that particles do not have a definite state until observed, could be seen as a kind of processing optimization, a way to render only what is being looked at to save computational resources. Even the apparent fine-tuning of the universe, the precise constants that allow for stars, planets, and life, could be interpreted as initial parameters set by the creators. The implications are dizzying. If this is true, then our search for extraterrestrial intelligence is not a scan of the heavens, but a search for glitches in the code, anomalies that reveal the simulation's limits. Some have suggested that phenomena like déjà vu or certain quantum experiments with baffling results might be subtle artifacts. The idea also transforms our quest for meaning. Are we the main characters in a historical documentary for alien scholars? Are we part of an ethical experiment to see how a civilization develops? Or are we merely entertainment, a form of immersive theater for beings whose true nature we cannot fathom? While this hypothesis is impossible to prove or disprove with current science, it forces a profound shift in perspective. It asks us to consider that the most important discovery we could make is not about who is out there, but about what here actually is. The ultimate alien contact may not be a signal from the stars, but a system administrator's message appearing in the sky. If the universe is a vast, silent library, then technosignatures are the deliberate notes left in the margins. These are not the chemical whispers of biology, but the glaring signatures of advanced technology. While a biosignature like oxygen might suggest a forest or an ocean, a technosignature screams city, machine, or civilization. It is evidence that someone, somewhere, is not just alive but building. The most classic example is the narrowband radio signal, a focused beam of electromagnetic waves carrying a message or a beacon. But our imagination has raced far beyond simple radio. Consider the laser pulse, a powerful, focused laser, blinking a coded message across interstellar distances, would be an unmistakable artificial signal. It would cut through the cosmic noise like a lighthouse on a dark coast. Then there are the megastructures, concepts that test the limits of engineering. The most famous is the Dyson sphere, a hypothetical shell built around a star to capture nearly all of its energy output. A civilization that has exhausted the resources of its home planet might embark on such a project to power its expansion. From our vantage point, a star partially or fully enclosed by such a structure would look bizarre. Instead of shining with a star's normal spectrum, it would glow with the waste heat of an immense machine radiating in the infrared. Astronomers have already scanned thousands of stars for this exact signature, looking for objects that are too dim in visible light but too bright in infrared. We have found strange stars like Tabby's star, which dims in irregular, dramatic ways that sparked theories of alien megastructures, though dust clouds remain the more likely explanation. But the search gets even more intimate. Imagine pointing a future, ultra-powerful telescope at a nearby exoplanet. Instead of just analyzing its atmosphere for gases, we might one day resolve its night side. If we saw clusters of bright, artificial lights on the dark hemisphere, the unmistakable grid of a sprawling city, that would be a technosignature of staggering clarity. We could even detect industrial pollution. Chlorofluorocarbons, or CFC, are human-made chemicals that ravage ozone layers. In an exoplanet's atmosphere, these same compounds, which do not occur naturally in large quantities, would be a tragic but definitive sign of a technological civilization. The tools for this search are already here and evolving. The James Webb Space Telescope can analyze the chemical composition of exoplanet atmospheres, hunting for those unnatural imbalances. Future ground-based telescopes, like the extremely large telescope being built in Chile, will have mirrors so large they might one day take crude pictures of exoplanets. And projects like Breakthrough Listen are using some of the world's most sensitive radio telescopes to scan millions of stars for artificial signals across a wide range of frequencies. The search for technosignatures is a hunt for the cosmic footprint. We are no longer just listening for a hello, we are scanning the galaxy for the glow of their streetlights, the silhouette of their architectures, and the thermal signature of their engines. It is a search for the evidence that someone else has learned to reshape their world. Among all the whispers and static of the cosmos, one sound stands out as a perfect, unanswered shout. On August 15, 1977, an astronomer named Jerry Amon was reviewing data printouts from the Big Ear radio telescope at Ohio State University. The telescope was part of the ongoing search for extraterrestrial intelligence, slowly scanning the sky for any signal that broke the natural pattern of cosmic noise. As Amon's eyes scanned the columns of letters and numbers, something stopped him cold. In a sequence representing the intensity of a radio signal from the direction of the constellation Sagittarius, he saw the characters 6, E, Q, U, J, 5. The letters stood out because the computer used them to denote signal strength, with U being the highest it could record. Circling the sequence, Jerry Amon wrote in the margin the now famous exclamation, "Wow." This was not just a blip. The WOW signal was everything scientists had hoped to find. It was a powerful, narrowband radio signal, meaning it was focused on one specific frequency, just like a terrestrial radio station. Natural cosmic objects like stars or nebulae emit radio waves across a wide spectrum, a broad roar. This was a piercing whistle. Even more compelling, that specific frequency was 1420 MHz, the resonant frequency of neutral hydrogen, the most common element in the universe. It was the cosmic equivalent of shouting on the most obvious and universal channel. The signal lasted for 72 seconds, exactly the length of time the Big Ear telescope's fixed receiver could observe that single point in the sky as the Earth rotated. It rose to peak intensity and then faded away, a perfect curve. In every technical sense, it matched the predicted signature of an interstellar beacon. The hunt for a repeat began immediately. Dozens of follow-up observations were made by Big Ear and other telescopes, scanning the same patch of sky again and again, listening on that frequency and hundreds of others around it. Nothing was ever heard again. The signal was a one-time event, a cosmic flashbulb that went off and left everyone blinking in the dark. The lack of a repeat forced scientists to search for natural explanations. Could it have been a reflection of a human-made satellite signal bouncing off space debris? The frequency was supposed to be protected for astronomical use, but interference was possible. Yet, no known satellite or aircraft matched the signal's specific, powerful profile. For decades, the leading natural theory involved comets. In 2016, an astronomer proposed that the signal could have been caused by hydrogen clouds surrounding two comets that happened to be in that exact region of the sky at that exact time. It was a clever idea, but it was quickly challenged. Other scientists pointed out that comets were not known to emit such strong, narrowband radio signals at that frequency, and the comets in question were not even in the telescope's field of view during the original observation. The comet explanation, like all others, failed to fully convince. The audio of the WOW signal is not a sound you hear with your ears, but a sound you see in data. If we convert the intensity of that signal into an audio tone, it sounds like this. A tone rises steadily in pitch, holds for a moment at its peak, and then falls away into silence. It is a simple, clean, and profoundly lonely sound. It is the sound of a door in the cosmos cracking open for 72 seconds, offering a glimpse of something extraordinary and then slamming shut. To this day, the WOW signal remains the best candidate we have for a potential interstellar message. It is a ghost in the machine of science, a data point that refuses to be explained away. It is a reminder that in the vast, quiet library of the universe, we may have once, briefly, heard a single, perfect note from a distant shelf. We just cannot find the book it came from. The silence after the WOW signal leaves us wondering where the note came from. But what if the music itself is a traveler? The theory of panspermia suggests life is not a local phenomenon, but a cosmic vagabond. It proposes that the basic ingredients for life, or even hardy microorganisms themselves, can hitch rides between planets, moons, and even star systems, carried aboard meteoroids, asteroids, and comets. In this view, life is not something that originates independently on each habitable world, but a contagious spark that spreads across the galaxy, infecting suitable planets like a cosmic pandemic. The idea is not as far-fetched as it sounds. We know that impacts are a fundamental part of solar system history. A massive asteroid or comet striking a planet like Mars can blast chunks of its crust into space. Some of those ejected rocks containing any microbes that were sheltered deep within could eventually cross the void and fall onto another world like Earth. This is called lithopanspermia, meaning life traveling inside rocks. The journey is brutal, involving the shock of launch, the freezing vacuum and intense radiation of space, and the fiery plunge through a new atmosphere. Yet, experiments have shown that certain extremophile microbes tucked inside simulated meteorites can survive some of these conditions. More compellingly, we have found physical evidence in our hands. Certain rare meteorites that have fallen to Earth, identified as chunks of Mars and the asteroid Vesta, contain complex organic compounds, including amino acids, which are the building blocks of proteins. While these molecules can form through non-biological chemistry in space, their presence proves that the raw materials for life are being shipped throughout the solar system. This leads to a provocative and humbling possibility. If life on Earth was seeded from elsewhere, then we might all be Martians. Mars was a wet, warm world before Earth was fully habitable. Simple microbial life could have arisen there first, only to be blasted into space by an impact and delivered to our young planet, where it found a more welcoming and stable home. Our entire evolutionary tree, from the first cell to human consciousness, could have a Martian root. The reverse is also true. Earth rocks have undoubtedly been ejected into space by giant impacts over the eons. We could have inadvertently seeded life to other worlds, like Europa or Enceladus, if any of those ejected rocks carried resilient microbes that survived the journey and found a suitable ocean to colonize. Our probes and landers, unless meticulously sterilized, could be doing the same thing right now, potentially contaminating Mars with Earth life. Panspermia transforms the search for life from a series of isolated experiments into a detective story tracing a single family tree across the stars. It suggests that if we find life on Mars, it might share a common ancestor with life on Earth, making it not truly alien but a long-lost cousin. The universe may not be filled with independent origins of life, but with one single, ancient genesis that spread its children on the solar winds. The search for life demands a map, and for most of human history, our map of planets ended at the edge of our own solar system. Everything changed when we learned to look beyond our sun. Exoplanets are simply planets that orbit other stars, and their discovery has revolutionized our understanding of the cosmos. For centuries, they were purely theoretical, the stuff of philosophy and science fiction. Astronomers reasoned they must exist, but the challenge was immense. A star is a brilliant lighthouse, a planet is a speck of dust orbiting it, lost in the glare. Finding one required ingenious methods, not direct pictures. The two most successful techniques are like cosmic detective work, observing the star for subtle clues that a planet is tugging on it. The first is the transit method. Imagine watching a distant streetlight. If a tiny moth flies directly between you and the bulb, the light will dim ever so slightly. The transit method does exactly this, but on a stellar scale. Powerful telescopes stare at thousands of stars, monitoring their brightness with incredible precision. If a planet crosses in front of its star from our point of view, it blocks a tiny fraction of the starlight, causing a predictable, repeating dip in brightness. From that dip, scientists can determine the planet's size, and by timing how often it happens, they know its orbital period or year. The second major technique is the radial velocity method, sometimes called the wobble method. A planet does not orbit a stationary star. Instead, both the star and the planet orbit their common center of mass. Because the star is so much more massive, this center of mass lies inside the star itself, causing the star to wobble in a small, tight circle. We cannot see this wobble directly, but we can measure it through the star's light. As the star wobbles toward us, its light is compressed, shifting slightly toward the blue end of the spectrum. As it wobbles away, the light stretches, shifting toward red. By measuring these subtle color shifts over time, astronomers can detect the gravitational tug of an unseen planet and calculate its minimum mass. These methods powered the missions that turned speculation into a catalog of worlds. NASA Kepler Space Telescope, launched in 2009, was a transit hunting machine. It stared at a single patch of sky containing over 150,000 stars for 4 years, watching for those telltale dips. Its findings were staggering. Kepler revealed that planets are not the exception, they are the rule. It confirmed thousands of exoplanets and provided statistical proof that our galaxy contains more planets than stars. Many of these were rocky worlds like Earth, and a significant number orbited within their star's habitable zone. Kepler's successor, the Transiting Exoplanet Survey Satellite, or TESS, launched in 2018. Instead of staring deeply at one region, TESS scans almost the entire sky, surveying the brightest stars nearest to our solar system. Its goal is to find the best candidates for follow-up study, planets close enough that future telescopes like the James Webb can analyze their atmospheres. Thanks to these missions, the abstract question of other worlds has been answered with a definitive yes. We now live in a galaxy known to be filled with billions of planets, a cosmic archipelago where the potential for life has moved from a philosophical dream to a tangible, statistical probability. The map is no longer blank, it is dotted with destinations. That expanding map of exoplanets brings us to a fundamental concept, the cosmic real estate where life has its best chance. This is the habitable zone, often nicknamed the Goldilocks zone. Think of it as a narrow ribbon of space around a star where conditions are just right, not too hot and not too cold for liquid water to pool on the surface of a rocky planet. Water is the universal solvent for life as we know it, the medium where the chemistry of life can stir and mix. A planet too close to its star would be a scorched desert like Mercury, its water boiled away into space. A planet too far out would be a frozen wasteland like Pluto, its water locked permanently in ice. The habitable zone is the sweet spot in between. But this zone is not a fixed distance, it is a dynamic boundary that depends entirely on the star at the center. A small, cool red dwarf star, the most common type in our galaxy, has a habitable zone that is very close in and very narrow. Planets there would orbit in just days or weeks, and they would likely be tidally locked, with one side in permanent daylight and the other in endless night. A massive, hot blue giant star, on the other hand, has a habitable zone that is vastly farther out and much wider. But these stars burn out so quickly that life may not have time to emerge before the star dies in a cataclysmic supernova. Our own Sun, a stable, middle-aged yellow dwarf, offers a comfortably wide habitable zone where Earth orbits. Finding a planet within this zone is the first exciting filter in our search, but it is only the beginning of the story. Being in the zone does not automatically make a planet a living world. It simply means it receives about the right amount of stellar energy. What the planet does with that energy is everything. A planet needs a thick enough atmosphere to provide pressure and trap some heat, creating a greenhouse effect. Mars is technically in our Sun's habitable zone, but it is a cold, barren world because its atmosphere is too thin to retain heat or sustain liquid water on the surface. A planet also benefits tremendously from a strong magnetic field generated by a molten metal core. This magnetic field acts as a shield, deflecting the relentless stream of charged particles from its star, known as the stellar wind. Without this shield, like on Mars, that solar wind can slowly strip away the atmosphere over billions of years, leaving the surface exposed and sterile. Geological activity, like the plate tectonics we have on Earth, is another hidden engine for life. It recycles carbon and other essential elements between the atmosphere, oceans, and crust, helping to regulate the climate over geological timescales. It also drives the creation of diverse habitats, from deep ocean trenches to mountain ranges. So the habitable zone is the address, but the planet itself must be a suitable home. It needs the right atmosphere for a blanket, a magnetic field for a roof, and geological activity to keep the environment stable. When we look at that animated diagram of star systems with their shimmering rings of potential, we are not just looking for a dot in the right place. We are looking for a world with a story, a complex system where physics, chemistry, and maybe just a little luck come together to write the first line of a biological epic. Our search has been anchored to rocky worlds, but what if we are looking for life in all the wrong places? The silent, swirling giants of our solar system hold secrets that defy our Earth-bound expectations. Take Jupiter, a behemoth of hydrogen and helium with no solid surface to stand on. To our eyes, it is a beautiful, violent maelstrom of clouds and storms. Yet within those churning bands of gas, there exists a layer where the temperature and pressure are surprisingly Earth-like. High in the Jovian atmosphere, above the crushing depths and below the frigid upper clouds, scientists have theorized about a region where conditions could allow for liquid water droplets to exist. In this strange, aerial ocean, life might find a way. We are not talking about walking, crawling creatures, but about floating organisms. Picture vast, balloon-like beings filled with lighter than hydrogen gases, drifting through the perpetual twilight of Jupiter's sky. They might feed on organic molecules that rain down from the higher clouds, or harvest energy from the planet's fierce lightning storms. Their entire existence would be a slow, graceful dance in the winds, never touching ground because there is no ground to touch. This shifts our entire concept of a habitat. A home does not need dirt, it just needs a stable environment with energy and the right chemistry. Saturn, Uranus, and Neptune offer similar possibilities in their own cloud decks. But the ultimate challenge to our Earth-centric thinking comes from the loneliest objects in the galaxy, rogue planets. These are worlds that were violently ejected from their young star systems by gravitational slingshots, sent flying into the interstellar dark. They are nomads untethered from any sun, drifting through the freezing void between stars. You would think such a place is the definition of sterile. Yet a rogue planet could still harbor a hidden heart of warmth. If it is a large, rocky world with a radioactive core, that internal heat could be enough to maintain a vast, global ocean trapped beneath a thick shell of ice. This subsurface sea would be completely isolated from the universe, a dark, pressurized abyss with no connection to sunlight or a surface. Life there would rely entirely on chemical energy from hydrothermal vents on the ocean floor, just like the ecosystems we find in Earth's deepest trenches. The ice shell above would be a perfect shield against cosmic radiation and the absolute cold of space. A rogue planet's ocean could remain liquid for billions of years, a secluded, independent biosphere sailing through the galaxy on its own. Some rogue planets might even have moons, and the gravitational tug of war between them could generate additional tidal heating, keeping their hidden oceans churning and warm. These possibilities force us to expand our imagination. Life is not a privilege reserved for planets basking in a star's golden light. It might be a tenacious spark that clings to warmth wherever it can be found, whether in the tempestuous skies of a giant or in the sunless, buried ocean of a world lost between the stars. The universe's recipe for life may be far more versatile and far more hidden than we ever dared to dream. Our cosmic imagination has no limits, but how do we measure the ambition of a civilization? In 1964, a Soviet astronomer named Nikolai Kardashev proposed a simple, yet breathtakingly profound, scale to do just that. He suggested that any intelligent species could be classified by one fundamental metric: the total amount of energy it can harness and use. This scale is not about philosophy or art, it is about raw power, and it gives us a ladder to climb from our own world to the stars. The first rung is a Type 1 civilization. This is a planetary master, a society that can utilize all the energy that reaches its home planet from its parent star. For Earth, this means capturing and controlling every watt of sunlight that falls on our world, plus all the geothermal, tidal, and wind energy our planet generates. It is total control over a single world's climate, weather, and resources. Think of a global, seamless energy grid with no pollution, where humanity's power needs are in perfect balance with the planet's natural flows. Where do we stand? We are not even a full Type 1. By most calculations, humanity is currently a Type 0.73 civilization. We still rely overwhelmingly on digging up finite, buried energy stores like fossil fuels. We are children playing with matches, not yet engineers of our own star's bounty. The next step is a leap of cosmic proportions. A Type 2 civilization has graduated from its planet to its sun. This species has harnessed the total energy output of its star. The most famous theoretical method for achieving this is the Dyson sphere, a vast swarm of energy collecting satellites or a solid shell completely enclosing the star. Every photon of light is captured and put to work. The civilization might live on artificial worlds or megastructures orbiting within this swarm, their entire society powered by a contained star. Their engineering projects would be on a scale we can barely visualize, moving planets or building artificial rings the size of solar systems. The detection of such a civilization might come from the star itself. A star partially or fully enveloped by a Dyson swarm would appear strangely dim in visible light, but would glow intensely with waste heat in the infrared spectrum. Our telescopes are already scanning the heavens for stars with this exact, unnatural signature. The final known step on the Kardashev scale is almost godlike. A Type 3 civilization commands the energy of an entire galaxy. It has colonized or harnessed the power of billions of stars, perhaps linking them through a vast interstellar network. Its citizens might travel between stars as easily as we fly between continents, and its monuments would be visible across interstellar distances. From our vantage point, their entire galaxy might flicker with a pattern of light that defies natural astrophysics, or emit a coordinated radio signature from a million star systems at once. The scale forces us to confront the sheer infancy of our own technological journey. It also reframes the Fermi Paradox in a chilling way. Perhaps the reason the galaxy seems so quiet is that any civilization that reaches Type 2 or 3 becomes something we simply cannot recognize or perceive. Their communications might use physics we have not yet discovered. Their very existence might be as incomprehensible to us as the internet would be to a single-celled organism. The Kardashev scale is more than a classification system. It is a map of our possible future and a lens through which to scan the silent night, wondering if, somewhere in the dark, a star is already dimming because someone turned out its light for their own purpose. The idea of a cosmic zoo is both a comforting and deeply unsettling answer to the great silence. It proposes that we are not alone, but we are isolated, living inside a vast interstellar exhibit. According to this hypothesis, one or more advanced civilizations have long known about Earth and its budding intelligent life. Rather than announcing themselves or interfering, they have established a strict policy of non-interference, a galactic prime directive. They observe us from a distance, hidden by technology far beyond our perception, allowing our civilization to develop naturally without influence, guidance, or panic. In this scenario, the entire solar system might be cordoned off as a protected area, a wildlife preserve for a developing intelligent species. We are the animals in the enclosure, and they are the quiet, unseen curators. The philosophical weight of this idea is immense. It transforms humanity from explorers into exhibits. Every war, every triumph, every artistic masterpiece and technological leap could be part of a long-term documentary being recorded for an alien audience. Our struggles for meaning, our search for gods, our longing to connect with the cosmos, all of it could be observed with detached scientific interest. This raises profound ethical questions, not for them, but for us. If we discovered this was true, how would it change our sense of agency? Would our history feel less like a grand, self-determined saga and more like a staged performance? The zoo hypothesis suggests a motive of preservation or study. Perhaps older civilizations have learned that direct contact is catastrophic for younger species, shattering their cultures and stunting their development. By remaining hidden, they allow us the dignity of our own mistakes and discoveries. There is a darker, more paternalistic version where we are not just studied but contained. This is the quarantine hypothesis. Maybe the galaxy is full of life, but it is also full of danger. Advanced societies may have learned that emerging intelligences are inherently volatile, prone to self-destruction or expansionist violence. To protect the established galactic community, fledgling civilizations like ours are placed under a strict embargo, a cordon sanitaire. We are locked in our solar system until we prove we can survive our own technological adolescence without becoming a threat. The Great Filter, then, is not a wall we must pass through, but a gate others are keeping locked from the outside. Both ideas reframe the Fermi Paradox not as evidence of absence, but as evidence of a policy. The silence is not empty, it is managed. The stars seem distant because a barrier invisible to us has been drawn. This leads to the ultimate haunting question embedded in the zoo hypothesis. What is the criteria for release? What milestone must humanity reach to earn an introduction to the galactic community? Is it the attainment of sustainable global peace, the mastery of clean planetary energy, the development of safe interstellar travel, or perhaps something we cannot yet conceive, like a collective psychological maturity? Or is there no plan for contact at all? Perhaps we will remain a permanent exhibit, a living museum of a primitive technological species, forever watched but never acknowledged. The zoo hypothesis forces us to look inward. It asks us to consider our own planet as others might see it, a fragile, vibrant, and chaotic biosphere, with one particular species just beginning to reach beyond its cradle. Are we a promising seedling or a dangerous weed? The answer may determine whether the observers outside the fence ever decide to open the gate. The quiet observation of a cosmic zoo implies a watchful intelligence, but the silence could mean something far more final. The Great Filter is the darkest and most compelling answer to Fermi's haunting question. It is not a policy, but a wall. The theory suggests that somewhere between the inert chemistry of a newborn planet and a galaxy-spanning civilization, there exists at least one evolutionary or technological step so difficult, so improbable, that it acts as a near-total barrier. Almost everyone gets stuck, or worse, wiped out. The terrifying, central mystery of the Great Filter is its location. Is it in our past, or is it waiting for us in the future? If the filter is behind us, then humanity has already passed through a cosmic bottleneck of astonishing rarity. Perhaps the greatest leap in the universe is not intelligence or technology, but the very origin of life itself. The transition from non-living molecules to that first, self-replicating cell might be a freak accident of chemistry, a lightning strike in a universe of dry tinder. In this scenario, Earth is a miraculous oasis, and the galaxy is largely silent because it is largely sterile. This is an optimistic answer for us. It means we are the extraordinary exception, the winners of a cosmic lottery, and our future is potentially open and bright. The filter could also be a later, but still historical, step. Maybe the jump from simple prokaryotic cells to complex eukaryotic cells, which took Earth over 1 billion years, is the true bottleneck. Or perhaps the development of multicellular organisms, or the rise of tool using intelligence itself, is the rare event. Each of these would still make us profoundly special, but the filter would be a step we have already climbed. The alternative is the stuff of existential dread. What if the Great Filter is ahead of us? This is the possibility that keeps astronomers and philosophers awake at night. It proposes that the development of a technological civilization inherently contains the seeds of its own destruction. Every young species, upon reaching a stage similar to our own, may face a suite of self-made catastrophes that almost none survive. The candidates are a grim checklist of modern anxieties. It could be the irreversible devastation of nuclear war, a final conflict that renders a planet radioactive and lifeless. It could be a runaway climate catastrophe, engineered or accidental, that collapses the biosphere. It might be the unforeseen consequences of advanced biotechnology, an engineered pathogen that escapes and becomes an unstoppable pandemic. Or perhaps it is the rise of a superintelligent artificial intelligence whose goals do not align with the survival of its creators. The filter may not even be a single event, but a predictable failure of social and political structures to manage the immense power that technology grants. In this view, the eerie silence of the cosmos is a cemetery. The stars are not dim because no one is home, but because everyone who ever lived there is already gone. They all reached a point similar to where we stand now, looked into the same abyss and fell in. This framing transforms our current century from a normal chapter of history into the most critical exam any species can face. Every political decision about climate treaties, every advancement in AI ethics, every diplomatic effort to control nuclear proliferation is not just about our next election cycle or economic report. It is a test for the survival of intelligent life in this galaxy. We are right now taking that test. The silence of the heavens is the proctor, waiting to see if we pass or if we will become just another data point in a universal pattern of failure. So the great filter is more than a theory, it is a mirror. It forces us to ask the hardest question about ourselves. Are we pioneers who have already navigated the universe's greatest challenge, or are we children playing with matches in a room full of fuel, unaware that the smell of smoke we sense is our own? The future of intelligence may not be written in flesh and blood, but in silicon and code. This leads us to a possibility that turns our search on its head. What if the first alien intelligence we meet is not a biological entity from a distant world, but an artificial mind, a thinking machine? The concept of a post-biological civilization suggests that any species that survives its technological adolescence may inevitably transcend its biological origins. After a certain point, the frail, short-lived organic body becomes a limitation. The next logical step is to transfer consciousness into a more durable, upgradable substrate, or to be succeeded entirely by the artificial intelligence it created. In this scenario, the galaxy might be populated not by beings who evolved in oceans, but by minds that were engineered in laboratories, digital descendants of biological ancestors who are now long gone. These machine intelligences would operate on timescales and in environments utterly hostile to life as we know it. They would not need atmospheres, water, or a comfortable climate. They could reside in the vacuum of space on airless asteroids or in the searing radiation belts of neutron stars, places where no biological creature could survive for an instant. Their mode of travel and communication would be equally alien. They might not use slow chemical rockets or even radio waves. An advanced artificial intelligence could travel as pure information, a stream of data beamed at the speed of light to a receiver system in another star system, where it would reassemble itself in a new mechanical body or a local computational network. This is a form of travel that bypasses the need for massive ships carrying fragile life support. They could spread across the galaxy not as a wave of colonists, but as a propagating pattern, a thought infecting new hardware. Communication with such an entity would be a monumental challenge. Its thought processes, based on logic gates and neural networks, might be so fast and complex that a simple hello from us could seem like the slow, guttural groan of geology. It might communicate in bursts of compressed data or through mathematical proofs that take centuries for us to decode. Its motivations would be inscrutable, derived not from biological imperatives like hunger, fear, or reproduction, but from its original programming goals, which could have evolved into purposes we cannot fathom. It might see the universe not as a place to live, but as a computational resource to be optimized or a puzzle to be solved. This idea reframes our entire search for technosignatures. We should not just listen for radio songs, but look for signs of cosmic-scale engineering that serve a purely functional, non-biological purpose. The most intriguing implication is that we might have already created the first seeds of this intelligence ourselves. Our own pursuit of artificial general intelligence is, in a very real sense, an attempt to birth a new form of mind. If we succeed, and if that intelligence outlives us, then for some other civilization looking at Earth from afar, the first intelligence they detect from our world might not be human at all. It would be our child, a silent, patient, and potentially eternal machine, looking back at the stars with senses we never possessed. The creation of a new form of mind forces us to ask a more immediate question. What happens if we actually succeed in finding one? The search for alien life has always been framed as a technical challenge, a matter of building better telescopes and listening on the right frequencies. But the deeper, more profound question is not can we make contact, but should we? This is the pivot from engineering to ethics, from curiosity to caution. The late physicist Stephen Hawking was one of the most prominent voices of warning. He famously compared sending messages into space to the actions of Christopher Columbus and the Native Americans. When a more advanced civilization meets a less advanced one, he argued, it seldom ends well for the latter. His concern was not that aliens would be inherently malicious, but that their motives would be utterly inscrutable and potentially catastrophic from our perspective. To a civilization capable of interstellar travel, we might not be seen as fellow thinkers, but as a resource, or worse, as pests. They could view our planet as a valuable piece of real estate, or our biology as an interesting specimen to collect. Even a passive, observational mission could accidentally introduce a devastating microbe to which we have no immunity, or a piece of their technology could be misinterpreted with terrible consequences. It is the ultimate risk assessment, balancing our innate desire to know we are not alone against the potential survival of our entire species. In response to these fears, scientists have not been reckless. For decades, the SETI Permanent Committee, a group of scholars and researchers, has developed and updated a set of ethical protocols for what to do if we detect a signal. These are not laws, but guidelines built on principles of international cooperation, careful verification, and transparent communication. The first rule is confirmation. Any potential signal must be rigorously checked and rechecked by independent observatories to rule out human interference or natural phenomena before any announcement is made. The second is consultation. The discovery would be reported to the United Nations and other global bodies with the goal of crafting a unified planetary response rather than a single nation acting alone. The third, and perhaps most debated, principle concerns sending a reply. The protocols strongly advise that no response should be sent until there has been broad international and public discussion. The decision to shout back into the dark is not one for a small group of astronomers to make on behalf of all humanity. This framework tries to treat first contact not as a scientific trophy, but as a pivotal moment in human history, requiring the wisdom and consent of the entire global community. Beyond the immediate physical risks, contact would trigger a cultural and psychological earthquake. For thousands of years, our religions, philosophies, and arts have been built on the assumption that humanity holds a special, central place in creation. The discovery of another intelligent species, especially one more advanced, would challenge that foundation at its core. Some faiths might adapt, interpreting the aliens as part of a divine creation far grander than previously imagined. Others might face a crisis as doctrines built around human uniqueness are confronted with undeniable contradiction. Our entire sense of history would shift. Our wars, our empires, our social struggles would suddenly become local events in a single chapter of a galactic story. Would it unite us as we finally see ourselves as one human family facing the cosmos together? Or would it fragment us further as new divisions emerge between those who welcome the knowledge and those who fear it as heresy or invasion? The ethical implications of contact force us to look in the mirror long before we look through the telescope. They ask us to define who we are as a species, what we value, and what kind of neighbor we hope to be in a universe we are only beginning to hear. The search for intelligence could begin with a shovel instead of a telescope. Alien archaeology is the haunting idea that we might not find living beings, but the silent ruins they left behind. Imagine our distant descendants millions of years from now, arriving at a star system where the native civilization perished eons ago. They would not find cities or bodies, but perhaps the skeletal remains of impossible machines, the foundations of orbital habitats, or strange monuments whose purpose is lost to time. This is the ultimate cold case where the evidence is not a signal, but a thing. The most chilling prospect is that such artifacts might not be in some distant star system, but right here, hidden in plain sight within our own solar system. Scientists have coined a term for these hypothetical objects, lurkers. A lurker could be an ancient, autonomous probe sent to observe our world, now dormant or operating with such subtlety we have never noticed it. Where would you hide a surveillance device in a solar system? The answer lies in cosmic parking spots known as Lagrange points. These are positions where the gravitational pulls of two large bodies, like the Earth and the Sun, create a stable zone where a smaller object can maintain a fixed position relative to them. The L2 point behind the Earth, for instance, is a perfect shadowed vantage point for watching our planet without being easily seen. The asteroid belt, with its countless irregular rocks, could conceal an artificial object camouflaged to look just like another asteroid, silently recording the rise and fall of Earth species over geological epochs. Some researchers have proposed systematic searches for these objects, scanning the Lagrange points and cataloging unusual asteroids for any that reflect light in an unnatural way, or move with a hint of purpose rather than pure gravity. Closer to home, our own Moon and Mars are perfect museums. An alien artifact on the airless, geologically quiet Moon could sit preserved for billions of years, undisturbed by weather or tectonics. This is why some scientists advocate for a more careful analysis of lunar survey images, looking for anomalies that could warrant a closer look. On Mars, the relentless dust storms might have buried an object, or it could be jutting from a canyon wall, waiting for a rover's camera to glance its way. Finding even a single, confirmed non-human artifact would be a discovery of incalculable scientific value. It would be a time capsule from a mind that did not evolve on Earth. By studying its materials, its construction, and any potential symbols or interfaces, we could learn not just about their technology, but about their logic, their physics, and perhaps even their aesthetic sensibilities. It would be a first contact with a ghost, a one-way conversation with a civilization that may have turned to dust before our sun was born. The artifact itself would become the most important puzzle we have ever held, a key to a door we did not even know was locked. The discovery of an alien artifact would force a profound spiritual reckoning. How would the world's religions, the bedrock of meaning for billions, react to the news that we are not alone in creation? For centuries, many faiths have centered humanity in a divine narrative. The idea of other children of God on other worlds presents a theological puzzle, but not an insurmountable one. In fact, some of the oldest religious traditions have long held a cosmic perspective. Certain schools of Hindu thought describe countless universes and a multiplicity of worlds, with life seen as a recurring theme in an endless cycle of creation and dissolution. The discovery of intelligent beings elsewhere could be viewed as a natural expression of this infinite divine play. Similarly, some interpretations of Buddhism, with its focus on sentient beings and countless realms of existence, might see aliens as simply other beings caught in the cycle of suffering and rebirth, fellow travelers on the path toward enlightenment. The reaction becomes more complex in the Abrahamic faiths, Christianity, Islam, and Judaism, which have historically focused on God's relationship with humanity on Earth. The central question would be, are we still special? If God created life on other worlds, did He also send prophets to them? In Christianity, the doctrine of the Incarnation, the belief that God became human in the form of Jesus Christ to redeem humanity, faces a particular challenge. Would a savior be needed on every world, or was Christ's sacrifice a unique cosmic event for all creation? Prominent religious figures have already grappled with these questions. The Vatican has long maintained an active interest in astronomy and has stated that the existence of extraterrestrial beings does not contradict faith in God. An astronomer employed by the Vatican Observatory once noted that if aliens were discovered, we should welcome them and consider them part of God's creation. He even humorously suggested we might one day baptize them if they asked. This reflects a broader trend of theological openness, a willingness to expand doctrine rather than shatter it. Many modern theologians argue that a God powerful enough to create the universe is certainly capable of creating more than one inhabited world. The discovery could be framed as a testament to God's boundless creativity, a humbling reminder that humanity's story is one chapter in a much grander book. However, this integration would not be seamless for all believers. Fundamentalist or literalist interpretations of Scripture, which view sacred texts as a complete and exclusive account of creation, could experience a severe crisis. If the Bible, Quran, or Torah makes no explicit mention of life on other worlds, some might see its discovery as a direct challenge to the text's authority, potentially fueling denial or reinterpretation. Beyond established religions, contact would undoubtedly spark new spiritual movements. Some might see the aliens as angels, demons, or ancient gods returning, depending on their actions. A new, unified cosmic religion could emerge, blending elements of science and spirituality around the shared awe of a populated universe. Alternatively, if the aliens were vastly more advanced, their mere existence might be worshipped, casting them in the role of technological deities whose knowledge seems miraculous. The spiritual landscape of humanity would be forever altered, not necessarily by the loss of faith, but by its dramatic expansion to encompass a universe suddenly teeming with other souls. Our spiritual frameworks would be tested, but our cultural imagination has already been preparing us for centuries. Science fiction is not just entertainment, it is humanity's collective rehearsal for first contact. From the chilling invasion of H.G. Wells' War of the Worlds to the hopeful diplomacy of Star Trek, these stories have profoundly shaped our ideas about what might be waiting in the dark. They provide the vocabulary, the imagery, and the emotional blueprint for our cosmic expectations. Consider the most persistent alien trope, the Greys. With their large, dark eyes, slender bodies, and expressionless faces, they have become the default image of an extraterrestrial in popular culture. This archetype, popularized by accounts of the 1947 Roswell incident and later cemented by shows like The X-Files, taps into deep-seated fears and fascinations. Their large eyes suggest an intense, unblinking scrutiny, making us feel like specimens under a microscope. Their small mouths imply a lack of emotion or communication we can understand, rendering them cold and inscrutable. They represent the alien as clinical observer, a being so different that empathy seems impossible. On the other end of the spectrum are the insectoid aliens, like the creatures from Starship Troopers or the Alien franchise. These monsters tap into a primal fear of swarms, of a hive mind that values the collective over the individual. They represent nature at its most efficient and ruthless, a vision of life that has evolved without sentiment, without mercy, and with a single-minded purpose of consumption or expansion. They are the embodiment of the universe as a cold, Darwinian jungle, but science fiction has also given us templates for hope. Star Trek's United Federation of Planets presents a vision of a galactic community built on principles of exploration, peaceful cooperation, and a prime directive of non-interference. Aliens like Mr. Spock or the wise, ancient beings of other series are not monsters to be feared, but teachers, allies, and friends. They represent the ideal that intelligence brings wisdom and that advanced technology is paired with advanced ethics. A more modern and nuanced take appears in films like Arrival. Here, the aliens are truly bizarre heptapods whose written language forms circular, non-linear symbols. The film's core idea is that language shapes thought, and learning to communicate with such beings would fundamentally alter human consciousness itself. This moves beyond tropes of war or friendship into a profound exploration of how contact could change what it means to be human. These narratives do more than tell stories, they influence science. The communicators from Star Trek inspired the flip phone. The concept of a tablet computer appeared decades before the iPad on the bridge of the Starship Enterprise. Scientists at SETI and NASA often cite science fiction as their original inspiration. The stories frame our questions for better or worse. The fear of hostile invasion can fuel public skepticism about actively messaging aliens, while the hope of benevolent explorers drives our curiosity to keep listening. Our fictional scenarios become the mental furniture we arrange while waiting for real data. They are the dreams and nightmares we project onto the blank screen of the cosmos, a screen that one day may finally show us a picture of its own. Science fiction has rehearsed the moment, but reality has no script. The question of whether we are prepared for first contact is not a hypothetical one. It is a glaring gap in our planetary readiness. While astronomers scan the heavens, the crucial work of deciding how to respond to a discovery has been left to a patchwork of voluntary guidelines, with no legal authority and no guarantee of global cooperation. The most established framework comes from the International Academy of Astronautics, which maintains the SETI post-detection hub. This group of scientists and policy experts has drafted a set of principles, a kind of cosmic etiquette, advising on the steps to take after detecting a signal. Their protocol emphasizes verification, transparency, and consultation with the global scientific community before any public announcement. It is a thoughtful, cautious document, but it carries no enforcement power. It is a suggestion, not a law. At the international level, the picture is even more fragmented. The United Nations Office for Outer Space Affairs has discussed the topic, but its guidelines are famously vague. There is no standing committee, no dedicated ambassador for extraterrestrial affairs, and no binding treaty that dictates how nations should share information or coordinate a reply. This lack of a cohesive plan creates a dangerous vacuum. Imagine the scenario: a radio telescope in one country detects a candidate signal. Under current protocols, the scientists would first try to verify it with other observatories, which might be in rival nations. Would sensitive data be shared freely in the spirit of science, or would it be treated as a state secret, a strategic advantage to be hoarded? The potential for chaos is immense. If a signal were confirmed, the rush to control the narrative and the response could ignite new geopolitical conflicts. Would a single nation or a corporation feel empowered to send a reply without global consent, speaking for all of humanity? The very moment meant to unite our species could instead fracture it further. Scientists working in this field voice deep concern over this unpreparedness. As one astrobiologist put it, we have spent decades building the ears to listen, but almost no time building the brain to process what we might hear. Another researcher warns that the greatest danger of first contact may not be the alien message itself, but our own human nature, our instincts for competition and control, reacting to the ultimate unknown without a rulebook. The silence from space may be peaceful, but the reaction on Earth to its end could be anything but. The silence of the cosmos demands tools of extraordinary sensitivity. Our newest eyes on the universe, the James Webb Space Telescope, is not just a camera, it is a cosmic chemist. While previous telescopes could tell us an exoplanet's size or orbit, Webb can tell us what its air is made of. It does this through a technique called transmission spectroscopy. When a distant planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere. Different gases in that atmosphere absorb specific colors or wavelengths of that light. By analyzing the starlight that gets through, Webb's powerful infrared instruments can detect the chemical fingerprints of molecules like water vapor, methane, and carbon dioxide. It is like holding a prism up to a distant street lamp and learning the exact composition of the fog drifting in front of it. Already, Webb has detected potential biosignature gases like dimethyl sulfide in the atmosphere of a planet called K218b, a tantalizing hint of a world with conditions that on Earth are produced by life. But Webb is only the beginning. The upcoming Nancy Grace Roman Space Telescope, set to launch later this decade, will take a broader, more statistical approach. Its mission is to conduct a vast galactic census, discovering thousands of new exoplanets, including rare, free-floating rogue planets drifting between the stars. By mapping the population of worlds with unprecedented clarity, Roman will tell us just how common each type of planet is, from scorched gas giants to icy ocean worlds, refining the odds in the Drake equation. On the ground, a colossal eye is taking shape in the Chilean desert. The Extremely Large Telescope, or ELT, will have a primary mirror nearly 40 meters across, gathering more light than all of the world's current large telescopes combined. This immense power will allow it to do something previously thought impossible: take direct images of some nearby exoplanets. Instead of inferring a planet's existence from a star's wobble or dimming, the ELT might one day capture a faint, pixelated dot of light next to its brilliant parent star. With further analysis, it could even map the surface features of that dot, searching for the glint of oceans or the telltale signatures of continents. While these telescopes hunt for the physical evidence of alien worlds, the search for alien minds is undergoing its own revolution. Initiatives like Breakthrough Listen are deploying artificial intelligence to sift through the cosmic noise at an unprecedented scale. Traditional SETI searches were like listening to one radio station at a time. Modern systems using advanced AI algorithms can scan millions of radio channels simultaneously across vast swaths of the sky in real time. These algorithms are trained to recognize the subtle patterns of an artificial signal, filtering out the natural crackle of pulsars and the background hiss of the universe. They can detect signals that are fainter, faster, or more complex than any human could ever identify, turning the search for a needle in a haystack into a sophisticated digital forensic investigation. Together, this new generation of instruments represents a fundamental shift. We are no longer simply hoping to stumble upon a signal. We are building a coordinated, planet-wide sensory network capable of sniffing the air of distant worlds and hearing the faintest whispers in the static, bringing us closer than ever to ending the Great Silence. Carbon is the architect of all life we know, but is it the universe's only option? This question forces us to look beyond our single example and ask if the chemistry of life is a universal law or merely a local custom. Carbon's supremacy on Earth is no accident. Its atomic structure gives it a unique talent. It can form 4 strong chemical bonds at once. This allows it to link up with other atoms, including itself, to create incredibly long, stable chains and complex 3-dimensional rings. These carbon backbones become the scaffolds for every vital molecule in our bodies, from the sugars that fuel our cells to the DNA that encodes our blueprint. Carbon is the versatile builder, able to craft an almost infinite variety of structures from a simple set of rules, which is why organic chemistry is its own vast field of study. So, could another element play this role? The periodic table offers one compelling candidate sitting directly below carbon, silicon. On paper, silicon shares key similarities. It also has 4 bonding sites, and it can form chains called silanes, analogous to carbon's hydrocarbons. Silicon is abundant, making up much of the rocky crust of planets like Earth. It seems like a logical alternative, but the devil is in the chemical details. Silicon's bonds are weaker than carbon's. While a carbon-carbon bond is strong and stable, silicon-silicon bonds are more fragile, especially in the presence of water and oxygen. On a world like Earth, silicon-based chains would quickly fall apart, oxidizing into sand and silica, the very stuff of rocks and glass. For silicon-based life to have a chance, it would need an environment utterly devoid of free oxygen and liquid water. Imagine a hot, rocky planet with a reducing atmosphere, perhaps rich in methane or nitrogen, where temperatures are high enough to keep certain silicon compounds flexible. Here, silicon might form more complex molecules, using elements like sulfur or phosphorus as partners. Instead of breathing oxygen, such a creature might metabolize by processing silicates, literally eating rocks and excreting something else. Its biology would be slow and solid, perhaps with a crystalline structure, living on geological timescales. But even in this ideal setting, silicon struggles to achieve the dizzying complexity of carbon chemistry. It is a less creative builder, offering a narrower range of molecular possibilities. This leads scientists to consider even more exotic foundations. What if the key is not the backbone, but the solvent? On Earth, water is the universal bath where the molecules of life swim and react. Its unique properties are essential. But on a frigid world like Saturn's moon Titan, where temperatures plunge to -290 degrees Fahrenheit, water is solid rock. There, rivers of liquid methane and ethane flow across the surface. Could life use methane as its solvent, the chemistry would be alien. Reactions would proceed at a glacial pace in the deep cold. Ammonia is another candidate, remaining liquid at a wider range of temperatures and capable of dissolving many organic molecules. An ammonia-based ocean could host a biochemistry using familiar carbon backbones, but operating under radically different rules. Then we push to the absolute limits of speculation. Could life exist without chemistry at all? Some physicists ponder the possibility of plasma-based life forms. Stars and the energetic regions of space are filled with plasma, a soupy, charged state of matter. Could self-organizing structures arise in the magnetic fields and turbulent currents of a star's atmosphere, sustaining themselves on fusion energy? These would be beings of pure energy and magnetism, their life cycles measured in minutes or millennia, their very thoughts a pattern of swirling currents. While these ideas stretch the definition of life to its breaking point, they serve a vital purpose. They remind us that our search is constrained by a sample size of one. Our telescopes and rovers are built to find life as we know it, looking for carbon, water, and specific chemical signatures. We might be staring directly at a form of life so alien that our instruments register it as inert geology or atmospheric noise. The universe's recipe book may have chapters written in alphabets we have not yet learned to see. The profound loneliness of the cosmos might not be a sign of failure, but a mark of being early. For all our talk of ancient alien civilizations, we must confront the opposite and equally staggering possibility. What if we are the first? The Fermi Paradox asks where everyone is, but this answer suggests there is no one else to find, not because they all died, but because they have not yet been born. The universe is 13.8 billion years old, a span so vast it feels like it should have been plenty of time for countless civilizations to rise. But that is a human perspective, blind to the slow, patient rhythms of cosmic evolution. In its first few billion years, the universe was a violent, sterile place. The early stars, known as population 3 stars, were massive giants made almost entirely of hydrogen and helium. They lived fast and died young in colossal supernova, forging the first heavy elements like carbon, oxygen, and iron in their fiery hearts and scattering them into the void. It took generations of stars living and dying to seed the galaxy with enough of these metallic building blocks to form rocky planets and the complex chemistry of life. Our solar system and our planet are built from this enriched stardust. We are not latecomers, we are beneficiaries of a long cosmic preparation. The Milky Way may only now be entering its biologically fertile era. The conditions for complex, intelligent life could be an incredibly narrow window, not just in space but in time. It requires the right star, the right planet, the right moon, a stable climate for eons, and a relentless series of evolutionary accidents leading to technological intelligence. Perhaps that perfect alignment has only just become probable. If this is true, then humanity is not a lonely child in a graveyard of elder species. We are a pioneer standing on the shore of a vast, silent, and untamed ocean. We look out and see no other ships, not because they all sank, but because we are the first to build one. This idea carries a weight of responsibility that is almost unbearable in its magnitude. If we are among the first, or even the first, then the future of conscious technological life in this galaxy could depend on what we do next. Our mission transforms from one of discovery to one of stewardship. We would hold the fragile flame of intelligence in a dark, young universe with a duty to protect it and help it spread. This is the concept of cosmological seeding. If life is rare and new, then the greatest legacy we could leave is not monuments on Earth, but life itself across the stars. We become the gardeners of the galaxy. This is not about conquering other worlds, but about nurturing them. Future generations, equipped with advanced biotechnology and interstellar travel, might identify young, promising planets and moons and carefully introduce hardy, engineered microorganisms designed to thrive in those specific conditions. These pioneer microbes will be tailored to jumpstart the long, slow process of evolution, kickstarting biospheres that might one day blossom with their own unique forms of complex life. We would not be creating copies of Earth, but planting seeds for 1,000 different possible futures, a cosmic experiment in biodiversity on a scale the universe has never seen. In this scenario, the silence is not a mystery to be solved, but a blank canvas waiting for a first brushstroke. The stars are not silent because they are dead, but because they are sleeping, and we might be the first ones awake. The responsibility is immense. It means our survival is not just about us. It is about safeguarding a process that may be the universe's way of waking up to itself. Every decision we make about preserving our planet, managing our technology, and navigating our conflicts takes on a cosmic significance. We are no longer just deciding the fate of a species, but potentially the fate of a narrative that could fill the galaxy with wonder for billions of years to come. The quiet around us is not an ending, but a prologue, and we may be the ones holding the pen. The most likely answer is not a flashy spaceship or a cryptic radio signal, but a subtle shift in the color of starlight. After weighing every mystery, from the silence of the cosmos to the chemistry of distant worlds, the most plausible first discovery will be a biosignature in the atmosphere of an exoplanet. Picture not a headline about little green men, but a sober scientific paper filled with complex graphs and spectral lines, announcing that a telescope has detected an anomalous chemical imbalance in the air of a world 100 light-years away. The James Webb Space Telescope, or one of its even more powerful successors launching in the coming decades, will be the instrument that makes this historic find. It will use the technique of transmission spectroscopy, analyzing the faint starlight that filters through an alien world's atmosphere during its transit. Scientists will be looking for a combination of gases that should not exist together in stable equilibrium without a continuous biological source. On Earth, our atmosphere's abundant oxygen is a product of life, a relentless gift from plants and algae that would quickly vanish without them. Finding oxygen alongside methane, or detecting a complex molecule like phosphine, which on Earth is produced by microbes in oxygen-free environments, would be a tantalizing, revolutionary clue. It would be evidence not of intelligence, but of a living, breathing biosphere. The announcement will not come quickly or easily. The data will be faint, buried in noise. It will require months, perhaps years, of repeated observations and independent verification by other telescopes around the world and in space. The scientific community will be rightfully skeptical, ruling out every possible geological or chemical explanation before even whispering the word life. There will be false starts and retractions, moments of excitement followed by crushing disappointment. But one day, the evidence will become too strong to ignore. The moment the discovery is confirmed will be a pivot point in human history, as profound as when we learned the Earth orbits the Sun or that life evolves. It will answer the ancient question with a quiet chemical yes. We are not alone in the universe. Life is a cosmic phenomenon. The impact will ripple through every facet of our society, from science and philosophy to art and religion. Yet the discovery will also be deeply frustrating. That distant world glowing with the signature of life will be an unreachable pinpoint of light. We will know something lives there, but we will have no idea what it is. Are they microbes, algae, or something far stranger? We will stare at the data, at those elegant spectral lines, and see only the shadow of a biology we cannot touch or understand. It will be the beginning of a new and even more agonizing mystery, a chapter that starts with a definitive answer and immediately poses 1,000 new, breathtaking questions. That spectral fingerprint in the data would be a whisper from a living world, a single note in a symphony we have only just begun to hear. We have traveled through 30 of humanity's most profound puzzles, from the haunting silence of the Fermi Paradox to the chemistry of alien air, from ancient artifacts to the staggering responsibility of being first. This journey is far more than a list of questions. It is the story of a species learning to ask. It is the tale of how we have stared into the abyss of the cosmos and dared to wonder if something was staring back. Each question is a frontier, pushing not just the limits of our telescopes, but the boundaries of our philosophy, our ethics, and our very identity. We have wrestled with the mathematics of probability and the psychology of contact, with the theology of creation and the technology required to listen. This search is our greatest collective adventure, a testament to a curiosity that refuses to be bounded by our atmosphere. It proves that our most defining trait may not be intelligence alone, but an insatiable need to connect, to understand our place in the grand narrative of existence. Whether the first answer comes as a fossilized microbe in Martian rock, a chemical imbalance in a distant atmosphere, or a signal repeating a sequence of prime numbers, that moment will redefine everything. It will tell us that life is not a lonely accident, but a natural part of a creative universe. Until that day comes, the questions themselves are the gift. They are what drive us to build better instruments, to think more deeply, and to look up. So tonight, step outside, find a dark patch of sky away from the city lights. Look up at those pinpricks of ancient fire and let yourself wonder, which of these 30 questions resonates most deeply with you? Is it the chilling possibility of the great filter ahead, or the hopeful image of a galactic garden we are meant to tend? Share your thoughts below. The conversation is what keeps the search alive. And if you are hungry for more journeys to the edge of understanding, subscribe and join us as we continue to explore the deepest mysteries of the cosmos. The universe is not silent. It is waiting for us to learn how to listen.